Good afternoon. We are looking at a most interesting and important video here. I am Mr. Ish. Thank you for joining me. I will be including a tag for another video where we've looked at the derivation of this formula right here using calculus. Here we're bringing all of those series, the power series, especially the Maclaurin series, into perspective as we will utilize that specific format to derive what you see right here before you. It's going to be very interesting. To do the derivation of this using the power series, especially in the Maclaurin series format, you need to understand these two things which I've shown you already in a previous video. Here I'm very quickly highlighting them. If you want to expand the sine x by means of the Maclaurin series, how would you go about doing it? You know how to do it. Let's very quickly look at it. You're looking here at a formula which looks like this: n equals 0 up to infinity. You have the nth order derivative 0 because we're looking at a Maclaurin series where a is always equal to 0. Very quickly, the 0 order derivative here, we're looking at basically sine x. The original function, you put 0 in it, you get a value of 0. The first order derivative, you're now looking at cosine, and then the 0, you're looking at a 1. The second order derivative, you're looking here at minus sine, and then 0. Placed in the a value of 0, you're getting a 0. The third order derivative, you're looking here now minus cosine, 0 coming into it, minus 1, and then the fourth order derivative, this is now going to revert back to your very original function sine. 0 coming into that, you have a 0. When you put all of these coefficients, because these are all representing this part right here, you develop your template, your expansion for this. We need the expansion for this and the cosine x to continue with that. You'll get a 0 as your first item. 0, x to the power 0 divided by 0 factorial. Then your next item is 1, x to the power 1 divided by 1 factorial. Your next item is a 0. X to the power of 2 divided by 2 factorial. Your next item here is a minus x cube. I'm not even bothering putting the 1, it's meaningless. 3 factorial plus a 0. When you clean this up, what are you getting? You're getting here as an x, then minus x cube over 3 factorial. You add more, the pattern becomes clear because I've shown this all in previous videos. X to the 5 over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial, on, and you know all of that. Now, let's look at the same exact everything here, but with regards to the cosine, because we need to know that. For the cosine x, you want to expand this out in terms of a series, Maclaurin series, a is equal to 0 in all instances, a equals 0. You have exactly the same format. Your 0 order function is equal to your original function with the 0 coming in. Its cosine of 0 is equal to 1. Your first order with the 0 is going to be now minus sine and 0, and that's a 0. Your second order with regards to your original, which is cosine x, is going to be minus cosine and then 0 coming in, it's a minus 1. Your third order with regards to the original is going to be here a sine and then 0 coming into that. You know sine of 0 is a 0. And then finally the fourth order derivative, which will cycle you back to your original, you'll be looking here at a cosine of a 0, which is going to be a 1. These right here will represent the coefficients which will come here, and now you can expand the series. It's not hard. You're looking here at your first item 1, x to the power of 0, 0 factorial. Then you're looking at a 0, x to the power of 1 over 1 factorial. Then you're looking at a minus x to the power of 2 divided by 2 factorial, then plus a 0 x cube over 3 factorial, and finally plus x. I'll put a 1 over here, 1 x to the power of 4 over 4 factorial. When you clean this out, what do you get? You're getting here as your term 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. And I've shown you this very recently. Your next item will be here, will be x to the power of 6 over 6 factorial, then plus x to the 8 over 8 factorial, on and on. What we will do is transpose this right over here, and then we'll now get to the actual meat of this video. So what exactly is it that we're really looking at right over here? What is this? This you know to be your Euler's formula, and that's exactly what we're looking here at, the derivation of this, but we're using a Maclaurin series expansion to derive the Euler's formula. You already know this was a Euler's formula, and now I'm just reminding you that it is that. How do you do this? It's nothing more than you doing a series expansion of something which was an exponential function here, except the exponential function is aix. That's what you're really looking at. Now, of course, you have to do your nth order derivatives. You know the exponential function derivatives are all the same. So the Maclaurin series route expansion for this is not hard. You have to look at the higher order derivatives of this. It's not a simple e to the x. You're looking here really at e to the ix. You're going to use this formula, e to the ax. Derivative of this is always a e to the ax. You'll see that each time this a value will come over here, and it'll be nothing more than imaginary number computations. That's all what it'll turn out to be. Let's bring these higher order derivatives into play. When you're looking at the zero order function, you're looking at e to the ix. It's just that. When you put a value here of 0, you're looking here at 1. When you do the first order derivative, this I comes here, you're looking at I e to the ix, but when you put a equals 0, this becomes 1, you're just looking at an I. Then the second order derivative, you do all of that, you'll look here at an I square, which will be minus 1. You can compute this, you'll see everything be, this shortcut is good. Here you'll get I cubed, which will be minus I. And then the fourth order derivative will be an I to the power 4, which will be 1. So you've gotten these, you've gotten 1, you've gotten I, minus 1, minus I, and then 1. You can now use this to start laying out the expansion of this exponential function we have over here, e to the ix. When you do it, look right here what you get. You have 1 x to the power 0 divided by 0 factorial plus I x to the power 1 over 1 factorial minus 1 x squared over 2 factorial. And then you have over here minus I x cubed over 3 factorial plus, here you'll have 1 x to the 4 over 4 factorial. You can extrapolate everything else over here. If you go from here, then the next item, which would be I to the 5, would be what? I to the 4 times I. I to the 4 times I would be 1 times I would be AI. Then you're looking at I to the 6 would be I to the 4 times I square, which would be 1 times minus 1, which would be minus 1. You see from here we continue on, you'll have a minus 1, then you'll have a minus I, then you'll have a 1. You see how I've extrapolated everything, because these are imaginary number computations. N equals 0, 1, 2, 3, 4, 5, 6, 7, 8. I'll go up to 8 over here, because then I can establish this series very well for you. I am here up to 4, then I have plus I x to the power of 5 over 5 factorial. Then I have minus 1 x to the power of 6 over 6 factorial. Then I have minus I x to the 7 over 7 factorial, and then plus 1 x to the power of 8 over 8 factorial. What are we doing again? We're developing the Euler's formula using the power series approach, specifically the Maclaurin series approach. Look at all the non-imaginary components and isolate them. I'm looking at these with their signs and then pluck them out. When you pluck them out, see what happens. I have here 1 x to the power 0 over 0 factorial minus x squared over 2 factorial. I'm removing these unnecessary coefficients, plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial. Here's my plus sign, which is going to come right over here. Now let's look at the imaginary number components. I have here an I x over 1 factorial. I have here a minus I x cubed over 3 factorial, and I can put a parentheses here. I have a plus I x to the 5 over 5 factorial. Then I have a minus I x to the 7 over 7 factorial, and then you know what the next one would have been, plus I x 9 over 9 factorial. Had I gone one more, that's what I've got. And there it is. Now what do? You can isolate all of this. We have the plus sign. Look right over here. When I'm looking at this, I'm seeing nothing here other than what looks like the cosine expansion, cosine x. Remember, in this entire video, wherever I have an x, I could have used a theta. X and theta are interchangeable, then thetas would come here instead of x. Anyhow, from all of this, I have a cosine x. From all of this, you look at here, you have an I. You can isolate the I. When you isolate the I, you can re-parenthesize everything here, but without the I components, because the I has been pushed out. You're just looking at everything else other than the I. That everything else looks very much like now your sine expansion. Then you have obviously the sine x. All of this is equal to what you have expanded, e to the ix. And that right there is your Euler's formula derived. And there it is. You've seen it. Remember here again, you can isolate the I and bring the I out right over here. Then you're just looking at x over 1 minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, on and on, which right there is your sine series. The development of the Euler's formula by means of the power series approach, specifically the Maclaurin series route, develops and extends from the expansion of the sine x and cosine x, because they are very much derived, or they are very much plucked out from the expansion of this specific function. When you expand this function, you see an inherent cosine series expansion and a sine series expansion, which you pluck out, you separate, and it comes right here into this form. And this form right here is perfect. Either the ix is indeed equal to cosine x plus I sine x, because their individual expansion series come into this derivation procedure. And that right there is the end of this video. Thank you for watching.